Good morning, everyone. Welcome. I hope everyone can hear me clearly. So I'm Robert Harris, and I'm the director of the Institute of Advanced Computational Science here at Stony Brook University. And certainly part of our mandate at IACS is to look forward to the future. And certainly quantum computing, the theme of this meeting, broadly construed, is central to that future. It's been very exciting to see across Stony Brook and also with our partner at Brookhaven National Lab, a very wide range of disciplines and individuals coming together to put together a very broad and fascinating story that touches on essentially all aspects of intellectual activity and research here at Stony Brook and again up at Brookhaven. And it's a privilege then to be introducing the first speaker for this meeting, Eden Figueroa, who I had the privilege of meeting for the first time, maybe nearly a year ago now. And I've constantly been excited and enthralled by the amazing techniques and his ability to manipulate matter and photons and other things at the very smallest scale to create exciting new technologies. So Eden is jointly appointed between Stony Brook University and the he's the founding group leader of the Quantum Information Technology Group here at Stony Brook University, and he's jointly appointed up at Brookhaven in the Computational Sciences Initiative and in the Instrumentation Division. He's been here with us since 2013, and before that he was in Garching, Germany, where he was a postdoc at the Max Planck Institute. And prior to that, he was a postdoc with, a PhD student in Calgary in the Quantum Information Science Department there. And so I'm now turn the floor over to Eden, who's going to discuss.
Thank you. Thank you, Robert. Well, first of all, I thank you all very kindly for coming to this event. This is an event that basically marks ramping up activities in the quantum area with a lot of institutional support from Stony Brook, right? So the more we are here, the more the points we can make. So I thank you very kindly. They asked me to warm up the crowd a little bit. So I was going to say a bunch of outrageous stuff during the next half an hour, so everybody remains awake, okay? So I want to start, and we decided to start a little bit talking about what quantum communication is, because quantum communication is something that everybody relates to. Right? As you will see, we're going to start ramping up the weirdness of the topics that we're going to be discussed through the day. So this is the one that we somehow relate to, and this is what we're going to start today. So this is what we're going to be discussing today. Three main messages that I want to discuss with you. Most of the talk will be dedicated to introduce the concept of quantum communication. Basically, what is what we're trying to do? What are the main problems that we want to solve? And how is that we want to solve them, all right? Basically, all the techniques, all the experimental devices, how do we put them together, and at the end, what is what we want to do with it, all right? So, and then hopefully I have time, and then I will just very briefly show you what are the activities in this area that we're having right now on Long Island, right? Stony Brook and BNL teaming together to build the first light matter-based quantum network in the United States, hopefully in the world, that I don't know, but that's where we're going, right? So first thing, look at that beautiful design. This is specifically what we're trying to do. Quantum information as defined by wave functions, impinging into collective excitation of atoms, exchanges their information, so then we can do long-distance communication of entanglement or qubits. All right, that's basically the main goal. So then we're going to start exactly in that note. Okay, so then we can start our introduction. A few things that everybody relates and that basically set the stage for all the stuff that we've been doing recently, right? So then normally when you communicate, you can do this in a variety of ways. By the way that has advanced the speed in which we can do all the processing of information these days and then contact your buddies in Europe or in Japan or in China through Facebook and WhatsApp and everything, it's due to optical communication. Right? So then basically in optical communication, what we do, we have lasers, and then we amplitude modulate these lasers, so we send pulses of light, right? And then depending on the amplitude and then the frequency, we can encode the information, so then you can send your pictures to share in Instagram, okay? And we learned how to do this already a long time ago, right? So in the 60s or so, all these techniques were developed, right? And then we were able to increase the speed of this. And then through the 70s, we started lining up lots of fiber optics, right? In the 70s and 80s, these fiber optics will then cross countries, they will cross oceans, and then they can communicate continents in such a way that then these pulses can go in the fiber, and because the fiber has little losses, you can go for hundreds and hundreds of kilometers and then decode the information in some end receiving station, right? Because we were able to develop all this infrastructure, optical infrastructure, now we were able to build, with help from all the people that were programming, you know, the networks, etc., to build the internet, right? So there would not be internet if we wouldn't have those optical networks, right? So then you see how we are advancing into this, right? And then, you know, one of the first goals of this quantum communication storyline is to build a new type of internet, right? Professor Jeff Kimball baptized it as the quantum internet, and this is what we're trying to build. How can you enhance the current internet that we have with quantum properties, okay? So this a little bit so then everybody can relate. Problem number one that we confront where we're sending pulses or something containing information is that at some point, right, people can no longer decode it because the signal is very weak, right? I hope everybody saw the Lord of the Ring movie, and then you see that, you know, when they are going to attack Helm's Deep, they make this repeater connection in which they start putting all the fires, and then by connecting all the fires, eventually they are able to talk to each other, indicating the presence of danger, right? In Africa, they do something similar, right? They have these instruments, and then at some point, somebody with very good hearing has to then just hear the weak signal and then reproduce it again, in a sense, kind of amplifying it, and in that way, you can make a link that is long, okay? In modern times, we still do the same, right? I have this picture there that you see. Basically, what we did is we have these long fibers, and then these long fibers, of course, they are not perfect. They have losses, and then the longer the distance you cover with your light pulses, the more losses you will get, right? Therefore, you got to put this picture that you see there is an amplifier that then amplifies the pulses of light in the middle of the ocean, right? This is why you can then make your Skype calls with your beloved ones if they are in Europe, for example, right? These classical amplifiers are the ones that then allow us to then just, by having some nonlinear medium, amplify these pulses of light without losing the information, and so it can keep going, all right? So then this is the version that we do from the classical world, and I think I can say this very well. It works great, right? This is why many things happen in the recent decades. So now, first slide in which we're going to touch upon something about quantum. The question is, well, I think we know how to do this classically very well, right? We can amplitude modulate, we can change the frequency, we can do everything. But then what happens if instead of trying to transmit these pulses of light that you can later amplify, now you're trying to transmit quantum information, right? So then quantum information is a little bit different because instead of having the normal zeros and ones that you encode in your amplitude of your pulses, right, TTL, 0 or 5, as we do in all electronics, now you want to send states that are now, instead of just a defined state, either 0 or 1, something that is in a superposition, or 0 and 1, okay? So good news, we know how to use light, right? We have developed for 4 decades all the technology to use light, so the only thing that we need to do is then push the technology a little bit forward, so instead of sending pulses containing millions and millions of atoms, now these pulses only contain 1 photon at a time, right? A photon is a quantum particle, so then it can be placed in a superposition of things. Something that you learn, for example, in your physics classes is that light has a polarization, right? So basically the polarization determines where the electric and the magnetic field are, and then how they're oscillating. So then depending on the position of these guys, this is what we call the polarization. So then the beauty of doing experiments with single photons is then that you can transmit it in these fibers, but now, instead of being on and off, now you have basically a photon that is either with a polarization in one way or a polarization in the other way, right? And then at some point you have to make a measurement to see what's going on with that polarization, right? So this is very important, and this is what this transit signal gives you. Once you have photons that have qubits encoded in them, right? So superpositions of polarization in this case, then you can have access to a plethora of new possibilities, okay? So the second thing that we want to do, and which is very particular to quantum mechanics, right? Here I introduce it more from an experimental point of view, right? So I'm an experimentalist. So say, yes, I can send photons that have superpositions of polarization, so I have my qubits, but what if I want to create states that are correlated beyond what one photon can do, right? And this is the principle of quantum entanglement, right? I have it there up there, right? So quantum entanglement is a quantum phenomenon in which quantum states of two or more objects have to be described with reference to each other, okay? So then the way we're going to do this, I describe it here in the experiment below. So we're going to start with a blue photon. You see what it says there, incoming blue laser light. And then this photon is going to have a polarization. It can be horizontal or vertical or a superposition between the two. And then what I'm going to do is I'm going to pass them through a nonlinear crystal there in gray. And then by a physical process, I'm going to be able to then break those photons, right? So those photons are blue, so they have a lot of energy. So then I can break that energy and create two red photons that I have there as two red cones, all right? So then I can preserve energy, so then those photons are now going to become red, all right? So then the properties of those crystals are going to allow me to then pick what polarization those photons have, all right? So then say, for example, if the blue photon hits the crystal number 1, and if it's horizontally polarized, it will give me two horizontally polarized photons, right? Now, if the photon is vertically polarized, it will pass the first crystal without doing anything, and then the trick that I'm going to play is I'm going to rotate the second crystal by 90 degrees, right? So then basically the photon will see a polarization axis rotated. So then if the photon is V-polarized, it then will create two vertically polarized photons at the end. Notice, and this is the beauty of quantum mechanics, if I start playing around games, and instead of sending a photon that has a defined polarization, right, a blue photon, now I send a photon that has a superposition of polarization, as I told you that we can do. So if, for example, it's 50% of the time is going to be horizontal, 50% of the time is going to be vertical, then because I don't know which of the crystals executed this process of dividing the photons, now I'm creating a superposition of having talked to the crystal 1 or the crystal 2. And this is what is going to then create a state like the one that I have on the right. See? So basically the output state is going to be either two photons that are horizontally polarized or two photons that are vertically polarized. But the beauty of this is that I cannot tell in a shot-by-shot basis which one of the two I have. Now, these states look cute and they look, charming. They are extremely important. They are the so-called Bell states. And those are at the very heart of what entanglement is, right? Why they are so important? Because if I make a measurement in one, then I specifically know what was the state of the other one, even though they are separated by a long distance, okay? And this is very important for us, remember? We want to transmit those photons over long distances. So then what can we do when we have first qubits and two photons that are sharing entanglement between them, okay? Now, remember, I saw when we have these classical repeaters, right? Basically, the only thing that we need to do is somebody that hears very well or some sort of box that is lying there at the bottom of the ocean. So then I can amplify this. In quantum mechanics, I cannot do that, right? If I send a photon and then, first of all, if I lose it because it's one photon. But then I cannot amplify the information that photon is carrying, that qubit, right? This is forbidden by the so-called non-cloning theorem, right? So then it means that I had to create a completely different set of technology if I want to do this, if I want to transfer information from one place to the other one. Why is this so relevant, right? Imagine that I have a source like the one that I show you that can produce those pairs of photons very, very rapidly, right? So for example, there I have 1,000 million photons per second, right? Many, 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 many photons. And then I put them in a fiber, and then I have Mehdi, my former grad student, right there, measuring the photons on the other side of the fiber. If the fiber is 1 kilometer long, he's going to be able to measure about 95% of those photons. So then the information will remain. That's good. If I do then 500 kilometers, even though I started with 1,000 million photons, he's only going to receive 1 photon every second. So then most of it is gone, right? And then if I do now 600 kilometers, then he will receive only 1 every 100 seconds. Right? This is due to all the losses in the fiber. If I just do 1,000 kilometers, which is not a crazy distance, right? It's, within the United States for sure. Then he will receive a photon every 300 years, right? So then instead of 1 grad student, you probably need 6 or 7 grad students measuring their, all their lifetimes. So then the question is, see, this is a really big problem, right? So how do we solve this problem? All right, so then remember, the tools that we have are going to be having qubits, having entanglement, and then doing some measurements. That's all we got, all right? So then this is what I'll explain in the following. Okay, so now, the question that the scientific community these days is trying to answer is, how can I transfer this entanglement, right? If I send 2 photons that are entangled over a fiber, do they remain entangled after covering lots of distance, right? That's a big question. And there's a lot of teams in the world that are actually working on this, right? This is a very hot field these days that is called quantum communication. How is that am I supposed to send those entangled photons and still have entanglement after propagating over long distances? There's been lots of experiments along the lines of this. Well, not lots, but a few. And particularly the teams in China, in USDC, they already have a small network, right, over some kilometers. The team in Calgary did a beautiful experiment there, connecting several buildings, right? There's teams in Vienna. There was this very famous experiment in Tenerife, right, in the Canary Islands, in which those photons are basically free to propagate in free space. In the other experiments, they are moving in fibers. Very recently, the Chinese government launched a satellite. So that satellite has one of these sources of quantum entanglement, that the one that I show you, and then those photons propagate in the atmosphere, and then they have stations, Shanghai, I think Tibet, where they can measure this, okay? But all of these experiments are subjected to what I told you. The more distance you cover, the more losses you have. And this is why those experiments are placed in Tibet, because you probably had to be a monk to be very patient to wait for those photons to arrive to your station, right? So then that's kind of like the stuff that we want to somehow bridge, okay? So there is 2 interesting applications of having transferred those photons over long distances, and this is why there is so much interest from governments to try to fix these issues, right? So then one of them, I will just describe it very briefly. This requires basically a whole presentation, but the idea is every time you send a message, right, the way we do these days, we use this one-time pad protocol, in which basically we have a message that is encoded with bits of information, and then what we do is we mix that one with a random key, right? And this is actually the message that is then transmitted, and then you can, by knowing the key, decode the information, right? This is very important because it's protected by basically mathematical complexity, and that's how we do all our credit cards transactions, okay? The problem here being, some people had thought, what happens if you have, you will hear about this later, right? Barry's going to tell us how to build it, actually. If you have a quantum computer that can perform tasks that are incredibly fast, maybe these encryption protocols are no longer valid, and then we have to think about something different. Well, if you were able to transmit those qubits of information, right, that are now going into these fibers, and then you want to send a message, the message can still remain classically encrypted, no problem, you have your bits. But now in this case, you will have 2 parties that will be exchanging, instead of a random key of bits, now they can exchange a random key of qubits, right? These are these photons that you see there. These arrows that you have there are actually the polarization. Remember I told you the photons, we can encode information in the polarization. And then this is very important. This is some very, very famous protocol that is called BB84, Bernard and Brassard 84, when it was originally devised. And then basically, by sending all these random states and then having the receiver doing also random measurements, you can demonstrate that if the system is quantum, if somebody is eavesdropping, you are able to tell, right? This is important. In classical communication, if somebody hacks your information, you only learn once your informations are already in somebody else's website. In this case, by doing quantum cryptography, you can try to do this sort of quasi-real time to then try to avoid this, okay? So this is a very important topic. And there's been a lot of developments in this area. There's already many companies that are working on this, national labs that are working on this over many parts in the world. The problem still remains, you can only do this over the distance permitted by the losses that you have in your fibers, right? As I was telling you. So the second story that you can do, right? So, this is a quantum mechanics lecture, so I need to put some equations, but no problem, okay? Once I add entanglement into the picture, I can do things that are not possible with classical communication, right? The first one that I want to tell you about is this protocol that is called quantum teleportation, okay? So in this protocol, in quantum teleportation, let's not think about much of the details. You start with 4 photons. Remember, I told you how to make 2. So you have 2 of those sources. And then what we're going to do is one of them, channel 2, we're just going to detect it, right? Because remember, those photons are always born in pairs. If I detect one, I know that I have another one. So then that one, which is going to be channel 1, is going to be carrying a qubit, right? A superposition of polarization. So then what I'm going to do, I'm going to have another entangled pair, in this case channel 3 and channel 4. And then what I'm going to do, I'm going to do a measurement between channel 1 and channel 3, right? And then I'm going to let channel 4 propagate over a long fiber. Now, this equation, it looks a little bit complicated, but the only thing that it wants to say is the state of these 3 photons together, if you write it all together in the space where they exist, it exists as a combination of states that are now, you see them here. You have a Bell state between, for example, photon 4 and 1, 4, 1, and then you have a qubit in photon 3, right? So then basically, at all times, the state of these 3 photons is described by this quantum mechanical object there. This quantum mechanical object, you see, if you are able to make a detection that then tells you that 4 and 1 were in a Bell state, this is what is called a Bell state measurement, then you can, because of the principle of quantum mechanics, project the state of the photon that is remaining there into the original qubit, right? So then basically, I start with a qubit, make a measurement, and then by doing a second measurement, even if I'm 1,000 kilometers apart, I can prepare that original photon that was entangled, right, 3 and 4, into the qubit that I have, right? This, of course, you cannot do classically, because then you cannot teleport that information like that, all right? So this is a very important protocol, because it will allow me to do then, communication in parallel, and perhaps at some point transfer large amount of data from one web place to the other one. All right? Maybe not tomorrow, but maybe at some point. So this is important because this uses the principles of quantum mechanics to perform this task. Okay? Here is a video that I'm reproducing with permission from the University of Calgary. Professor Barry Sanders at some point had a program on the visualization of quantum mechanics. This is going to show you how this quantum teleportation protocol works. That pink thingy there is a pulse of light. Oops. Oh, no, not working. There you go. Good. Right? So that's a laser pulse, the one that is encoding the polarization. Then you have those crystals in which we are creating those photons. Right? They interact the way I told you. Then we create the 2 pairs of photons appearing in green, sharing entanglement by this wiggly line in green. We produce a second pair, as I told you. We let those guys run. Here, we're going to detect one of the first entangled pair in that gray box, which is a detector. So when I detect this, I prepare a single photon state that I pass through a polarizer to create a qubit. And then what I'm going to do a measurement between this qubit and one photon from the other entangled pair, right there, right? When my detectors click, I can then project the state of these 2 into a Bell state, which immediately projects, right, the state of the other qubit, the other photon, into a qubit after I perform a measurement in that polarizer, right? So if that photon did 1,000 kilometers long, I can still prepare that qubit in that superposition. If I were to have 1,000 entangled photons, then I will be able to do, with this protocol, perhaps lots and lots of information very quickly. Okay, so then that's one of the things that we want to do. Now, second thing, what happens if I want to cover this entanglement over long distances, right? What happens if I don't want to do experiments over 2 kilometers where these things work and it has been proven, but I want to do it over hundreds or maybe thousands of kilometers? Here, I have to use another principle that is called entanglement swapping, Right? So in this protocol, what I want to do is by starting with two entangled photons, akin to the teleportation protocol that I show you, right? Now what I want to do is a measurement between channel 2 and channel 3 without killing one of the other photons like I did in the teleportation. And then what I want to do is entangle photons that at the beginning were not entangled, right? This we can do again because of the power of quantum mechanics. We can write the full quantum state of these 4 photons as a superpositions of states that are basically a function of these Bell states that we described. So then if I make a measurement in 2 and 3, and then I can project that pair into a Bell state, for example, that psi plus, then that will mean that automatically photon 1 and 4 that at the beginning were not entangled, now they get projected into a Bell state, and now they are entangled, right? So basically we are creating entanglement out of a measurement, okay? Very important protocol, originally devised already a couple of decades ago by Professors Briegel and Soller. How does that work? So then basically what we want to do, right, we want to communicate information between, in this case, A and Z, right? And we want this distance to be very long. I know I cannot do it directly because I'm going to have losses. So then what I'm going to do is I'm going to start putting, instead of only one entangled pair and then communicating over fibers, now I'm going to have 2 entangled pairs. And what I can do is I can do my measurement there between D and W, therefore entangling A and Z, right? If I want to cover longer and longer distances, then what I can do is put more of these entangled sources and then do this entanglement swapping protocol as many times as I can, right? So then basically, remember, entangled these days is considered like a currency. So then by throwing money at it, throwing entanglement at it, I can actually create large rates of entanglement over really long distances. Right? So this is a genius idea. Please go and check that paper. This is really, if we can implement this, this will be something really, really cool. Okay? Now, here you see that there's a couple of issues, right? So basically, these measurements in which then I can project the states, so then I can entangle then the particles, are going to depend whether or not I can detect that state. And I cannot detect that state all the time. It is actually kind of like a probabilistic story. So then, very good. So then if I want to do this over longer distances, then what I need is a device that will allow me to synchronize all those measurement events between one and the next one, so then I can do this, okay? So this is what is called, this is basically 6 years of my research, it's called a quantum memory, right? A quantum memory is a synchronization device that will allow me to take those photons that are carrying entanglement. I can then store them, in this case, in an atomic cloud. Right? So I send them, store it, then I can wait for some time, and then the quantum information is going to be stored in this atomic cloud. And then after some time, basically waiting until the other Stelberg measurements in my communication line work, then I can then retrieve these guys. And then if I can do this, synchronize everything properly, I'm going to be able to then enhance the rates in which I am detecting entanglement, right? Quick video, so then you see how these memories work, right? I click once. Wait. Oops. There we go. Photon goes in there. I use lasers to manipulate the atoms. I can then store the information in the atoms, keeping it frozen in there. And then at some point I switch all my lasers back again. The photon comes out, and then I can do my Bell state measurement in all these places. Okay? Now, remember now, 2 important concepts here, entanglement swapping and quantum memories. The next video that has been produced at the University of Geneva by Professor Jessan will then let us know how this works. There you have your entangled source, entangled pairs as we discussed. We store them in a quantum memory. I have a similar system on the other side, another source with 2 quantum memories. I wait. I know all these quantum memories work. I can do then my Bell state measurement, keep those photons propagating, right? Now over longer distances. And then I can repeat this by putting more and more and more quantum memories over there, all right? And then this, if I keep doing this, as long as I have enough resources in terms of entanglement and quantum memories, I will eventually going to end up with entanglement share over long distances, okay? So that's basically the idea of this. Remember, very important concepts. Building that machine, this is what is called building a quantum repeater that is going to perform, let's call it amplification of the information that doesn't violate the non-cloning theorem, okay? In the last 3 minutes that I have remaining, I will give you a brief overview about what are the activities that we're doing here, and then please ask the panelists. They are the ones that are helping us build all this story here. I'm just very briefly, I'm going to fast forward through 6 years of my research and a 10-year process later. Here in Stony Brook and BNL, we have already built, and we are keep increasing, one of the largest quantum networks like the one that I showed you in the video, right? Remember in that video it says that at the very least you require 4 memories and a couple of entangled sources to do this. Well, this is precisely what we have built in my lab here in Stony Brook. We already have these sources of photons that we can interact with the memories. We have built already 4 memories, and we have all detection systems that would allow us to perform this, right? So then basically we're gearing up for a big experiment in which we want to make that repeater work, right? Some of these already received some publicity. You know, even the New York Times had a little bit of time to say, some guys in Stony Brook are trying to build that quantum network. Okay, so anyways, this ties, I'm going to make my publicity here for the Department of Energy, right? In the last year, the Department of Energy got into a really big impulse into try to being a large quantum network that connects many of the national labs. All these fibers already exist. The only thing we have to do is enhance it with the technology that I just showed you, and then maybe we can start communicating entanglement between California and Long Island, or the Long Peninsula. So this is exactly what we're building now together with Brookhaven National Laboratories. People have been very kind. I list the names there. We are building a second laboratory like the one we have in Stony Brook now, in which then we can store entangled photons on the BNL site. And at the moment, together here, Dimitri is going to tell us more about this later, we're trying to build a link that allows them to send those photons from the Stony Brook campus to the BNL campus. It might sound like science fiction, but it's actually not. Hopefully, by the end of this year, we're going to have the free space link working between the 2 campuses, so we can try one of these teleportation experiments. The idea will be then to use the fiber networks that are already available that go from BNL to New York City, and then Stony Brook to New York City, to then try to communicate to the rest of the United States if we can make that quantum repeater work. But I mean, we're trying. Here in Stony Brook, I don't know, maybe you have seen undergrad students carrying things that look suspicious. Possibly there are my students bringing quantum memories and entangled sources all over campus. So that's exactly the map as we have it. You see we have the physics building. When we have entanglement, that bold type means entanglement. The atoms guy there, they will look quantum memories. We got permission from the DOIT department to basically install them all over and use their fiber, which is great. Thank you, OVPR, for allowing us to do that. And then basically now we're going to try to connect to some tall building on campus that allows them to have a direct observation link to BNL. And then we want to exchange those photons and then have a similar network in BNL so we can do that. All right? So this is the current status of the project as we have it. We already did some preliminary quantum networking experiments in BNL that connect already 3 different buildings. Photons are flying there. Last week we were able to transfer entanglement over 16 kilometers. Kind of looks like we can do it, right? This is in development. SBU quantum network is already set. We are installing all these devices. And because all this is going very well, we got a new partner very recently. Yale is also wanted to play ball with us. So then we want to make this first prototype of a quantum repeater network that connects the 3 campuses, right? Distances are already enough to then try to prove this long distance communication. And the way it looks like is like this, right? This is the last slide of the talk, so then we're done with this, right? Stony Brook, here is where we're going to have some entangled sources, right? And then what we're going to do, remember in this experiment, you need 2 entangled sources. Then 2 photons from the 2 independent sources will be stored here in Stony Brook. We need to store them for about 300 microseconds, the time that it takes for the photons to fly from Stony Brook to BNL, a little bit longer from Stony Brook to Yale. Then in both Yale and in BNL, we're going to have 2 more quantum memories, as I show you in the repeater story. And then by doing a Bell state measurement here in Stony Brook, the idea will be to prepare an entangled state between BNL and Yale covering approximately 50 kilometers, right? And then, so that's our story. This is where we're sitting there. As of last week, my students are already building that prototype that you see on the back. So this is being built right now in the physics building, and in a couple of months, we're going to start building these links and then trying all this story. So anyways, as you can see, there's a lot of stuff going on. If you want to participate in these experiments, this is the whole point of this immersion workshop. Come and talk to me. There's a lot of stuff to do, and there's a lot of great experiments that are coming ahead. So thank you very much for your attention. I know it's very early. Thank you very much.
Okay, so we'll commence the panel session. So Eden, please.
Thank you.
And so I'm going to invite each of our panel members in turn to maybe introduce themselves and to comment on either their own interests or upon Eden's presentation. And so I'm going to start with Mehdi. Yes.
Good morning, everyone. I'm Mehdi. As Eden said, I'm his former PhD student and currently the CEO of QNect LLC. So my passion was slightly different. What I wanted to see was whether quantum information technologies is now ready to go beyond research base. So while I was his student, we got funded by NSF to go out there and see whether there is any need for these type of technologies. So we didn't assume that we made some cool stuff in the lab, so everyone should love it. We just went out there and we talked to more than 200 different people, potential customers, people in different fields, from engineers in Mercedes-Benz, for example, to different banks, financial firms, to see whether these people have problems that we can address and we can use quantum information technologies to help them. One of the main reasons we are doing this, one of the main reasons we want to go more towards the industry direction is because this whole workshop is here to put, so for the BNL and Stony Brook University to bring all the best engineers and scientists together to push this field forward. We want to expand this further. We want to bring people from industry. We want to bring people from various different fields, probably had nothing to do even with quantum, but people who can be very useful to help us move forward, from private investors, from different sectors. So one of the things we're now doing is that we have made a team of more than 12 people. Majority of them are business or legal advisors. So there are people who initially barely knew anything about quantum, but now after working with us for a year or two, they're very interested, and their expertise in different fields of business managers or managing or economic development is helping us a lot boosting forward these technologies. Soon we got some initial fundings from Department of Energy, and now we're talking with the private sectors to start investing in these technologies so we can bring as much fundings and resources to Long Island, to QNect, to these research facilities. And yes, it's been more or less around 2 years that now we've been doing this and going forward as strong as possible to not only develop the research site, but also have a development center here that we have at CVIT Center. So we don't want to just do research. Of course, the main focus here is to develop the research, but we also want to make these devices usable, make everything portable, anything that Eden has made in his lab so far. Now we are putting everything in boxes and make them ready to be used in real networks outside for fiber communications or free space communication. I think that most probably sums it up. Yeah.
Very good. Thank you. Paul.
Yes. Hi, good morning. I'm glad to be here, although it's maybe a bit surprising. So my name's Paul Stankus, and I know many of you in the audience. In my career to date has been in nuclear and particle physics, so this is a completely different story as to how I wound up working on quantum communications. So I'll just mention a few things along the way. So starting in particle physics, quantum mechanics totally rules the roost because quantum field theory is the standard technology, but no one ever really talks about elementary quantum mechanics and things like entanglement and superpositions and so on. So it's interesting to come back sort of a full circle. About 10 years ago, I developed an interest in astronomy and cosmology and started collaborating with the Brookhaven Cosmology Group. And the reason I got interested in quantum information was particularly because of an astronomy paper that I wound up reading that talked about using quantum teleportation and quantum memories to enhance the astronomy technique of single photon interferometry. And so after this, I read up on it in quantum networking and entanglement swapping and all these things. And it was just this whole new and interesting world, and sparked this new idea in two-photon interferometry that I'm working on now, which is sort of a cross between quantum networking and astronomy. And it's been like a great sort of flowering garden that has applications in remote entanglement distribution and also in astrophysics in possibly gravitational waves and exoplanets and all sorts of things. So it's been this surprising synergy coming from a completely different field, never expecting to get back into quantum mechanics as a technique, but once you start to think about it, inspired by something, these things just pop up and all these interesting techniques and possibilities. So it's gratifying to be here, and it's just an example of how you might never have expected it coming, but once you start to think about it, there are all kinds of applications and benefits.
Dimitri.
Good morning, everybody. My name is Dimitri Katramatos. I'm with the Computational Science Initiative at Brookhaven Lab. My background is in computer science, and actually my undergraduate studies were in mechanical engineering. I only mention this because it will become relevant later on. About 3 or 4 months ago, I was presented with a very exciting problem. I've been doing networking research at Brookhaven Lab, classical networking, software-defined networking, high-performance networking, and I happen to have some experience in what the network at Brookhaven looks like. So I was asked to help with putting together this quantum network that Eden was mentioning, and it came down to having multiple aspects and phases. First of all, we put together a short distance network between the physics building and the information technology division building and the instrumentation division building at Brookhaven Lab. And the main goal there was to use the existing infrastructure, the existing fiber infrastructure of the network, of the campus network of the lab, to do quantum communications. And this is exciting and terrifying because this network has never been designed to handle quantum communications. Everything actually happens at different wavelengths that the whole quantum story works. And we were very concerned that we won't be able to do anything because of the expected losses. However, we did put it together, and with the help of some magnificent people at Brookhaven Lab, we put it together pretty quickly and did several experiments. And the long story short is that it works. And I think we were able to see coincidences, and Andre will tell you more about that. But the losses were not the problem. Noise from the ambient lighting was. At the wavelengths and the powers that regular communications work, none of these problems seem to be significant, but when we are looking at single photons at a different wavelength, it becomes really important that you darken everything and dampen the noise so that you can actually see the single photons. Then we are looking at building a free space link, and there is a lot of things to take into account, and we had to find and survey several places at the lab. And at Stony Brook, it's pretty easy where the free space link is going to be built because you have this very high tower. But at Brookhaven Lab, it was not really obvious, so we had to survey several locations. And we did find a place that has line of sight with the tower, and this is what we're working on now. We're trying to build these instruments and put them on the roof. And further out, we're going to be looking into connecting Stony Brook and Brookhaven with fiber from a local provider that will be local, and in the far out in the future, we're looking into integrating ESNet's network that will take us from Brookhaven to Manhattan, and then NicerNet from Manhattan to Stony Brook, and which would be about 200 miles distance. And we want to do all these entanglement experiments over the long distance fiber.
Good morning, everybody. I'm Andrei Numerotsky from the cosmology group in the physics department of BNL. So I'm a high-energy physicist, so my background is there, and I worked in the past at large colliders like at CERN and at Fermilab. But I came to BNL to work on another kind of frontier of high-energy physics, cosmic frontier, to build a large synoptic survey telescope, the camera for this device, and so that's my day job. So instrumentation-wise, my interest was always in the silicon detectors, and for the colliders, I was building vertex detectors to register the vertices of decaying particles. For LSST, BNL is responsible for the CCDs, so we're building modules for the 3 gigapixel camera, and so that will go online pretty soon, actually, in about a year. So now, simultaneously, it occurred to me that you can combine fast properties of required for the colliders and good optical sensitivity in the same device, in the same sensor, and we came up with this idea of fast camera, something that has high quantum efficiency and nanosecond scale timing resolution. So that was another thing that I developed at BNL, and we started to use it in ion imaging experiments, for example, and also fluorescent lifetime imaging. So it has single photon sensitivity, and then after reading a couple of papers, on this quantum information science, and I contacted a good friend of mine, Alex Lvovsky, and who is a big name in this science, and asked him, so can we do something about it? And he pointed to Eden and told, oh, you have this great guy with a great lab just next to you. And so that's how we started to collaborate with Eden about 2 years ago. And we ended up writing a seed grant proposal and got seed grant, actually, BNL Stony Brook seed grant about 2 years ago, and that kind of kick-started this activity there. So since you need to detect single photons, pairs of single photons, so good time resolution is important there because you want to find a coincidence, and that's an important handle to suppress the background. And we conceived a few experiments, and actually did some experiments based in Stony Brook, using the camera. More than a year ago now, we published a paper, presented that. And then, of course, about a year ago, DOE also was very interested in these activities, and so it's very kind of good and very exciting that all this started to propagate. So now we have much larger project, more people involved, as we've heard, and we were doing experiments last weeks, actually, with good results. We were planning to publish them, sometime soon, and so I think it's important that now, kind of hardware-wise, this activity is also moving to BNL, so we're building a lab there, and we'll have good results soon. So I think that's my story.
Thank you. So just briefly talking about my own interest and what brought me here, very much like Paul, I started off from a domain, in my case, theoretical chemistry, that employs quantum mechanics as its main tool. And so we essentially solve the equations of quantum physics to predict what the electrons are doing in molecules, and thereby predict and ultimately design and control new molecules that have interesting properties and relevant, say, to clean energy programs, say, looking at new photovoltaic systems or new catalysts to make chemicals in clean and efficient manner. So these calculations end up being very large and expensive. So my sort of primary interest in quantum computing is actually as a consumer. I'm certainly very interested in getting my hands on effective quantum computers and understanding even how to use the imperfect devices that we have now to solve real problems in chemistry and material science. And this is actually one of the key areas that industry sees as an early success. So if you see presentations from Microsoft and Google, they'll list maybe 2 or 3 big applications. One is certainly encryption and security. Another one is big data, and we'll be hearing more about that this afternoon. But certainly a third that you'll see from these big giants are applications in chemistry and materials. And superficially, you'd ask why are they interested in this, and it's really because they understand the economic importance of being able to solve problems accurately and efficiently in these spaces and anticipate very many people coming to use and purchase their services once they have viable quantum computers. But what's also clear and what makes a strong contact with Eden's presentation is that an effective quantum computer, of course, needs an effective quantum memory associated with it. It's inefficient to get data from the classical world into the quantum computer. So once it's there, you need to keep it, and you need to be able to, you need a large quantum memory to run many already understood quantum algorithms. And you also clearly need eventually a quantum network to move this information around. Of these things, perhaps the most real is actually the quantum network and the quantum memory. The quantum computers are coming, they've been demonstrated, but they've got a long way to go before they're really usable. So now we still have a few more minutes, and so first of all, I'm going to invite the audience to have an opportunity to ask some more questions. Otherwise, we'll start prodding the panel with questions of my own. Yes?
I'm Emilio Mendez from both Stony Brook and Brookhaven. The question to the panel, and perhaps more specifically to Eden, is what are the big challenges the quantum communications face? Are they hardware related? Are they software related? From the hardware, it seems to me that everything is done. You have a source, you have a transmission medium, you have detectors. Are there any challenges associated with the sources, or what are the big challenges? Are more engineering or scientific challenges?
All right. Thank you for that excellent question. I was actually having this conversation with some people in BNL last week about it. So maybe I was very positive in my talk, and it kind of looks like most of the hardware is already in place. I think at the moment, as you saw there, most of the resources that need to be applied to do this is in the sources and in the memories. So then, you know, as Mary was saying, through developments that we have, we're trying to cover the memory part, but I think the scaling and making those single photon sources push button, right? So in a sense that when you send an electrical pulse or so, those two entangled photons come, it's still a challenge, right? Most of the technology that we use, for example, in my lab to do these entanglement sources, it is probabilistic, right? It only works sometimes, so then you try to make the rates very fast, but it still is not fully deterministic. So the main challenge, and I think it touches upon material sciences, is to still develop materials and systems that allow us to create, instead of, say, just one entangled source that works every now and then, hundreds of entangled sources that then you can put and correlate with the fiber systems that we already have, together with the memories. And then you can make these 1,000-kilometer communication aspects. So some of the stories that we are trying to develop together with the people in BNL is to really look in what other devices we can try to do to create these entangled sources. So one of the possibilities is to use to do quantum dots, and at the moment we have already a few ideas together with the condensed matter, Matt Dover here from Stony Brook, how to tune them in situ, such that after growing several hundreds of quantum dots, you can tune them individually, so then they generate at the frequencies that you need to operate with the memories, and if you can tune them very well and precisely, have hundreds of sources coming out from material science. So I think this is, in points of science, this is where the science problems are. And then hopefully once we solve this, certainly all these 4 memory, 2 entangled sources we can do. We should do it to drive it. But 5, 10 years from now, we are going to need new sources that allow us to then build larger and larger networks.
Yeah, to follow up, Eden, so I think scaling up is a big problem, and that's something that needs solution, and so that's, for example, why using the cameras instead of single photodiodes, as we do now, so that's a way to the scalability, because basically you can correlate photons in each pixel to each pixel, so that brings multidimensionality to the single photon detection. So another thing I want to mention is this, it's clearly the networking will be done with optical photons, which has EV scale energy, but most promising kind of other promising qubit systems are superconductive, which is milli EV energy. And so to scale up computers, for example, via quantum networks, you need to transduce this energy, and somehow interface qubits in two completely different systems. So that's another big challenge.
So in your wildest dreams, how many qubits per second do you expect to be, would you hope to be creating along this Yale, SBU, Stony Brook, and BNL network in 2 years' time? And be ambitious. I'm not going to hold you to it.
Yeah, so this is something that we're developing right now. So those material-based sources can operate with the tens of gigahertz. And we are, QNEC is developing memories that can operate at that speed. This is where we went into this direction, room temperature quantum memories, because room temperature quantum memories don't need preparation time, so you can operate them very fast. So, the target will be to hit the 10 gigs, so then, some of the electronics to control these are already available, in the 4G, 5G networks. So if you ask about my wildest dream, that's what I would like to do, right? But this is why we have everybody here, because in order to get to that dream, we need help, right? And this is what we are asking people to help us with their talent, right? But that will be my answer to your question.
Hello. Yes, Vahid Ranjbar, Brookhaven National Lab. I was just wondering, it's obviously easier to use photons as a base for all this, and so there isn't any obvious advantage to using other materials, but just out of curiosity, for communication, have they considered using electrons or other materials to propagate the quantum information? Has that been explored at all?
I'd say, to my knowledge, when you're doing experiments with electrons, normally you try to confine them, right? So then they can interact strongly between them. So normally when you talk about, I think people have discussed these quantum networks of electrons, but in the context of small crystals in which you have different, for example, vacancy centers that are talking to each other. So then you can do the talking with pulses containing electrons maybe, but that only works in small distances. So that could be very effective, for example, to do quantum processing locally. But if you eventually want to go and then communicate this, to some lab in Europe or so, you still need to do the photons. And this is what Andre was saying, right? So basically, this is good, right? We know how to do it, so that's fine. But then the transducing elements that will then bridge these two different physical systems, this is stuff that still remains to be researched, right? How can you do this transducing efficiently so then you don't lose all your information while changing physical systems? So they are good, but I think they are good for short distances. Very fast, actually. So you can process information real quick locally.
I think there's one last question.
So maybe this is also following on the same theme. I'm Mary Bisha. I'm from the physics department at Brookhaven Lab. In the electrical transmission, there's also now R&D on using superconducting transmission lines. So this is not in communication, but it comes from another field. Does that, and of course we know that some of the implementations of quantum computers are based on superconducting states. So those, like quantum dots and so on. Is there any synergies between that effort and using a different form of communication that is not photon-based, but could be, again, the electron-based using superconducting transmission lines?
So I was recently in this talk, and the IBM folks were basically discussing about this. In order to increase the potential of their systems, they want to make small networks that have several of those little quantum processing units, and they are connected to superconducting lines. So basically what you're mentioning is true, you can do it, but then I may say from my point of view,
if you really want to go longer distances, eventually you have to transfer these very efficiently to some photon, right? So this is basically one of the key elements that I think there's a lot of potential to be researched is, how do you do this transduction? If you actually look into the quantum memories that we build, we do this all the time, right? Because we convert photons, as I show you in those videos, into collective excitations of the atoms that actually happen in the hyperfine states of atoms, which are gigahertz separated. So in principle, if we were to couple very efficiently those quantum memories, atomic superpositions, to superconducting structures, we can probably do this transfer very efficiently. But then, you know, that's one of the experiments that we want to build in the lab in BNL, right? So that's coming. So give us a couple of years, and then I'll tell you more about it.
Okay, good. And I think now we should thank Eden and the other panelists again. Thank you.